Now we have seen fundamental theorem of linear inequality. Now we see that using the theorem we can derive some satisfiability conditions. Using the previous theorem we can prove two theorems of for conditions of satisfiability. What's the purpose of having conditions of satisfiability? Such that we can produce certificates when things are unsatisfiable. So let's see how that whole thing works. So let's suppose you have a matrix A and a vector B, right? And you have this constraint x greater than or equal to 0. You want to see if ax equals to b, and so and if this is true, the theorem says this is true if and only if for all y the following holds. The y a greater than or equal to 0 implies y b greater than or equal to 0. Okay? So how do you prove that? The first we see the forward direction. Let's suppose we have a satisfying assignment such that x naught is greater than or equal to 0, such that ax0 equals to b. So what do? You just multiply with y. If you multiply with y, then you say ax naught equals to yb. Now if this guy is greater than or equal to 0, we have x naught also greater than or equal to 0, therefore yb must be greater than or equal to 0, and that is this statement. And we are done in the forward direction. In the reverse direction, let's suppose there is no such x, and we will show that we also have a violation here. So a1 to an be columns of A. So a1 to an be columns. So consider the matrix A as bunch of columns, and you have a x. Okay, x is a vector here, which multiplies with these columns and produces b. All right. So you can see that x is defining the non-negative linear combination of columns to produce b. So you can treat them as you call that m vectors of from which you wanted to express b. So using that theorem 1, we can say that since the b is not in this cone, as we have seen that there's no such x, then we can use this theorem, and there is a y such that ya greater than or equal to 0 and yb is less than 0. Means you can take all these vectors and multiply with some c. We call that c is y here, so that c of all vectors gives you greater than or equal to 0, and if you multiply with b, then it should be get less than 0. Therefore you have this theorem holds true. So how this theorem is useful for us to proving unsatisfiability? This works as follows. We find y such that this thing holds, and y becomes my certificate that this constraint is unsatisfiable. When a solver gives me back that okay, this constraint is unsatisfiable, it should give me back this y, and this is act as a certificate of satisfiability. So let's look at an example, get more intuition about this theorem. So let's suppose our a is 1 1 1, and you have x1 x2 and equals to 3. This is the same equation, and if we apply the theorem 13.3, just the previous theorem, then you can easily see y times 1 comma 1 greater than or equal to 0 implies y times 3 greater than or equal to 0. You can easily check this thing holds all the time. So therefore there is a solution of x1 plus x2 greater than or equal to 3 where both numbers are non-negative. You can easily see that that is true. Let's look at the opposite condition, when you can clearly see that x1 plus x2 equals to 3 equals to minus 3 has no solution such that x1 and x2 both are greater than or equal to 0. So how this theorem fares up in this case, you have a is 1 1 1 and b is minus 3. Let's try to apply this theorem. Is there a y which violates this statement? Okay, yes, there is a y. Simply picking y equals to 1. If you pick y equals to 1, that simply says that this theorem does not hold. So this formula is unsatisfiable. So y equals to 1 becomes a certificate of your unsatisfiability. We can further extend this theorem to fulfill linear inequalities. Now I'm not saying x is positive or negative. Some x, okay, and ax less than or equal to b is more powerful statement. And if and only if the following holds: y greater than or equal to 0, ya equals to 0 implies yb greater than or equal to 0. Well, how do I prove it? I will use the previous theorem to prove this, okay, using a slightly clever trick. The trick is this: I will define something called a prime, where you have I, a, and minus a matrix written like this, and I will solve this constraint: x prime equals to b with x prime greater than or equal to 0. And you can easily see that if the solution is here, if and only if solution is there. Why that is so? So let's see, if I, a, and minus a, so if you think about it, it has three parts to it. Your unknown vector, you have a vector x prime, let's say x1 prime, and then you have x2 prime and x3 prime, and both are saying less than equal to, equals to b. If you multiply it, you find the x1 prime plus a x2 prime minus a x3 prime equals to b. And it's further simplify, get x1 prime plus a x2 prime minus x3 prime equals to b. Since this x1 prime has to be greater than or equal to 0, I can write this equation of a x2 prime minus x3 prime less than or equal to b. Now these two are both non-negative numbers, but the subtraction can be any number. So basically any integer can be represented as a difference of two non-negative numbers. So you can say you have some variable ax less than or equal to b. So this, if this is satisfiable, then this is satisfiable, and then you have equals all over the place. Now the statement is in the same format as the previous theorem. So you can use the previous theorem to make the following statement: that for all y, y of this matrix greater than or equal to 0 implies yb greater than or equal to 0. Now let's try to simplify it. It gives me y greater than or equal to 0, ya greater than or equal to 0, and minus ya greater than or equal to 0 implies yb greater than or equal to 0. So you see, I'm saying ya greater than or equal to 0 and the minus ya greater than or equal to 0. That means ya is 0. Okay, so then we get ya equals to 0, and then get this statement. So let's look at the unsatisfiability case, and then how in this situation I use this theorem to produce my certificate. So let's suppose we have these three constraints. When I'm saying all these x1 and x2 are both are less than or equal to 0, and there's some supposed to be greater than or equal to 3, which is not possible clearly. So write them in a matrix form, then you get A is this and B is this, and then you apply our theorem. Then we find that y is equal to 1 1 1, and then which is greater than or equal to 0, and if you multiply by a, you will find it to be 0. If you multiply with 1 1 1, so what you get, if you just take this and sum these columns, it gives you 0. If you multiply and this column, it gives you 0, so it gives you 0 0, right? And similarly, if you do yb, so y multiplies with this guy, okay, this thing, it gives you minus 3. And now this thing violates our theorem, therefore y is an evidence that this constraints are unsatisfiable.